Hello, everyone. I'm Billy Younger again. This is me trying to show you how to do a calculation to find out basically how long it'll take you to get to Mars. When we actually take off from Mars to or from Earth to go to another planet like Mars or to maybe the moon or something, we don't just randomly shoot off the ground, get in orbit, and then kind of look for the thing in the sky and drive to it, hit the accelerator or whatnot. Turns out that would be very, very expensive. And in the late 80s, for instance, it cost about a pound of gold for every pound that you sent to outer space, and that includes all the stuff that you have to send, which would be like fuel, spacecraft, food for humans, machinery, all that stuff. So it's very, very cost prohibitive to go to space in general. So what we try to do is make the most efficient path to a particular planet or to a particular body or something along those lines. In the case of a trip to Mars, we'd be using something called the Hohmann transfer. And the Hohmann transfer is basically where you establish an elliptical orbit where the short side of the orbit, in other words, the perihelion distance is actually the distance from the sun to the earth, and the long side of the orbit, which is called the aphelion distance, is actually the distance from the sun to Mars. In doing so, we're actually sort of getting a free journey because we're actually in an orbit around the sun. Of course, we only use the first half because we're going to take the first half and then we'll arrive hopefully at the moon when the moon, I mean, excuse me, at Mars when Mars gets there. And then, of course, later on, we'll have to make sure everything's set up right again for us to leave Mars and take the second half of the orbit back. So this gives you a little idea of basically how long such a journey would be, what the conditions must be for the positions of Earth and Mars upon takeoff from Earth, as well as what the positions between Mars and Earth would be upon takeoff from Mars. So I'm going to walk you through some of the calculations, but what you got to realize is there's a lot of different data we could use. For instance, the Earth, remember, is not in a circular orbit, neither is Mars. Although they're very close to circular, they have a smallest distance, a largest distance, and an average distance. So we're going to actually use all three in considering those. But remember, for the spacecraft that we're traveling in, we're always going to make an orbit where the perihelion distance is one of the distances from the sun to the Earth, and where the aphelion distance is one of the distances from the sun to Mars. So let me show you how we go about doing that. I'm going to first start by sharing my screen to show you the lab that Dr. Wright wrote up, and then I have, of course, modified over the years as well. So this is Dr. David Wright from Tidewater Community College, my boss, or formerly my boss. He just retired. Good for him. So this is the Hohmann transfer. You can see this would be like the Earth's orbit, and this would be Mars's orbit. And you see you take off in an orbit around the sun. Remember, the sun has to be at one focal point, not the center. It's going to be at the focal point. And then, of course, you can see that the perihelion distance, when it's closest to the sun, is the distance from the sun to the Earth, and the aphelion distance, which is the farthest distance, is when this it's when we go the distance between the sun and Mars. So we're going to take off here, we'll land here, and we got to make sure that when we get here, of course, Mars will be there. And then when we get there, we also got to make sure we have the right speed. So the process is a little convoluted, but basically we take off from the Earth. Then we make sure our speed is set properly, because what's going to happen is we drift further and further away, or use gravity to go further and further away. Conservation of angular momentum suggests it will slow down, but we got to have the right speed here so that we will end up at this location. And then when we get there, our speed's going to be slower than it was here, specifically because we're farther from the orbit, according to Kepler's second law. So then we got to adjust our speed again to make sure we can match the speed of Mars so that we can land on it. So we first have to consider, where's the Mars going to be located when we take off. Then we got to do the same thing on the way back. We got to figure out where should Mars and Earth be located so that when we take off from Mars, we'll hit Earth when it's there, and all that good stuff. But it's pretty simple, surprisingly how simple it is. With basic algebra, you can sort of calculate the fundamentals of the orbits. So what we're going to use here is repeatedly, we're going to use Kepler's third law. We're going to use these distance. The Earth perihelion distance is 0.98 AU, and the Earth's aphelion distance is 1.02 AU. Again, that's astronomical units. So these are both data about Earth's orbit. Then Mars's perihelion is 1.38 AU and its aphelion is 1.66 AU. These are both data about Mars's orbit. The spacecraft is going to have a mixture of those two. It's going to have a perihelion distance that's one of these, or the average of these two top ones, and it's going to have an aphelion distance that's one of these, or the average of these two. We're also going to need to use an equation to tell us how the speed ranks. And you'll see that as you're doing this lab, the answers are often printed in subsequent parts so you can make sure you did got the right numbers and did the right calculations. Transfer time is just the time from takeoff to landing at the other planet. So it's literally half an orbit. But we'll also need to, like I said, calculate the speed at which an object should go. And for that, we'll use this formula. And it's important to remember that the speed that any particular object will go while it's in an orbit is 30 kilometers per second times the square root of 2 divided by the distance the object is away from the sun at the time, minus 1 divided by the semi-major axis of the orbit of the object. Okay, so it's important that you remember this is semi-major axis of the orbit of the object, which the semi-major axis is the distance all the way across the Hohmann orbit. That's the major axis, and then you divide that by 2, which I think you can tell is the aphelion distance plus perihelion distance. Add those two, you divide it by 2, and that will get you the semi-major axis of the actual orbit of the spacecraft. So we'll use that. Later, it gets a little more complicated. We're actually giving you everything you need with all these angles and stuff. And really, all you got to do is fill in the gaps of the actual lines. So, for instance, it says compute the period of Mars's orbit. This is just a Kepler's third law thing. Hey, I give you that the semi-major axis is 1.52. What is the period of Mars's orbit? And you put it in there. But later on, it gets a little more complicated, but it's literally saying, hey, look, we're using orbit 3. So that's not this data, but this data. That's orbit 3. We're using orbit 3, and we want to write down the transfer time, which remember was half the period, and the period of Mars. And you're literally just going to divide the transfer time by the period of Mars and multiply the answer by 360 and put it right there. Here again, it looks really confusing. Oh my gosh, what am I going to do? But they're literally saying take 180 degrees and subtract from it the angle Mars moves during transfer time. Well, that's just this number that you calculated here. So you're just going to do 180 minus this number and put it in there. Again, we're going to do transfer time, and this time divided by the period of Earth. And then we're going to multiply that by 360. And then instead, we're going to subtract 180 from that answer, and that'll give us the A at arrival. So it seems a lot more complicated than it is, but if you just follow the instructions, hey, put in the transfer time, hey, put in the period, divide transfer time by period, multiply by 360 using your order of operations, then you subtract the 180, and that'll get you that. And ultimately, what you'll be able to figure out is the wait time. In other words, the amount of time you have to wait on Mars. Because when you get there, you can't just pack your crap back up and go. It's actually a bit of a time you have to wait before the orbits get in the right, or the planets get in the right position so that you can depart properly. So there's a wait period, plus there's a transfer time there, a transfer time back. So the shortest period you could possibly get is this transfer time plus wait time plus transfer time. So that's ultimately the biggest answer you're going to get from all this until you get to the questions. Now, in the questions, I actually do give you a link. You can cut and paste that. That's to a story that aired for another time today. The first question asks you a relevant question about what you just learned. Same thing with the third and fourth questions. And as I normally do in my classes, I want you to answer all these in line. Right here, you put an answer, but I want you to type it in with a different color font. In other words, I prefer red, blue, or green. So you maybe take this, highlight it, start typing your answer, and then change the font color to red, something like that. So I think that gives you an idea of what we're doing with this lab. All this stuff will be ultimately saved. If you need to do any calculations to show me what you did by hand, then you can take a photograph of them and insert them in the document near where you're told to do the calculation. All the answers should be typed in here in red, blue, or green text so that they stand out from the regular text. And if you do any diagrams you have to draw or something like that, by all means, take a photograph of them and stick them in there as well. When it's all said and done, I want you to do File, Save As. Well, first I want you to just do Save. And then I want you to do File, Save As. And this time you're going to change the Word document to a PDF like that. And that's what you're going to turn in. I hope that helps. So let's stop the share right now. And let me discuss how we're going to go about doing this. So we've got basically a document camera that I'm going to show you basically the same orbit we just had. And I'm going to work out the calculations that we just did so that you can see how we're going to do this. So first off, it gives you some information. It gives you some data about Earth. It gives you some data about Mars. And it tells you a little bit about the Hohmann transfer, which is the key to understanding all this. So it says that for the Earth, we have, and I think you can see this. Let me double check. Yeah, you can see all this. So for the Earth, we have a perihelion distance, which I'm going to call pH, of 0.98 AU, and an aphelion distance, which I'll call AH, and that's equal to 1.02 AU. And then for Mars, we have pH again and AH again, but in Mars's case, it's 1.38. Again, these are astronomical units, and aphelion is 1.66. Okay, AU. And they've given us that P squared, and this must be in years, by the way, is equal to A, and that must be in astronomical units cubed. So we're going to use that equation. Later on, they'll also give us that the velocity is equal to 30 kilometers per second times the square root of 2 over r minus 1 over a. Okay, again, this is the distance from the sun for the object at the point in its orbit, and this is the semi-major axis for the object's orbit. So that's what we're trying to calculate here. Well, that's what we'll be calculating later. So one of the first questions they ask you is they're telling you we're going to use in orbit 1, we're going to use the fact that we are leaving Mars and arriving at Earth both during perihelion. In other words, it's sort of the quickest of the quick. We're leaving Earth when Earth is closest to to the sun, and we're going to arrive at Mars when Mars is closest to the sun. So that should make the smallest Hohmann transfer orbit possible. So the first question they ask is, what is the perihelion distance? What is the perihelion distance of the spacecraft? So the spacecraft is going to go in a Hohmann transfer orbit that looks like this. It's going to leave from the Earth and arrive at Mars. Okay, so you can see, obviously, its aphelion distance is the distance to the Earth, and its perihelion distance is the distance to Mars. But in that case, we're using perihelion to perihelion. So it says, what is the perihelion distance of the spacecraft? Well, that's when it's closest. And since we're going from Earth at its closest to Mars at its closest, then we're going to use 0.98. So 0.98 astronomical units is the perihelion distance of the spacecraft. And hint for this orbit, orbit 1, the perihelion distance is equal to the perihelion distance for Earth. So they even gave you a big hint. Hey, it's that guy right there. Use 0.98. And that's the way it continues, Mr. Lab. And now it says, what is the aphelion distance for the spacecraft? So remember, the aphelion distance is the longest distance, which again, in this case, is from the sun to Mars. But again, we're taking the orbital part that we're in for Mars when we get there, and we're going to pretend that's at perihelion. So I'm going to use the shortest of the Mars distances, which is 1.38 astronomical units. So that's the second part to question 1A. And now it says, hint, for this orbit, the aphelion distance is equal to the perihelion distance for Mars, which is exactly what I used. And then lo and behold, it shows 0.98 and 1.38, which is exactly what we got for our answer. So that's a check to make sure we did it right. So part 1B says, what is the semi-major axis of the spacecraft? And it again gives you a nice little helpful hint. But in general, remember the way orbits work is the orbit is basically an ellipse with the sun at one focal point. So I'm going to draw roughly an ellipse. And this one's going to be the aphelion distance. And this one's going to be the perihelion distance. And you see that if you add this aphelion distance and this perihelion distance, you get the semi-major, or excuse me, you get the major axis. But if we want the semi-major axis, then that's just half of that. So I just need to add these two, aphelion plus perihelion, and divide that answer by 2. That's all we got to do. So in this case, we're going to take 0.98 and add it to 1.38, and we'll of course get, if it was exactly 1, it'd be 2.38. So it turns out to be 2.36. So 1B is going to be 2.36 AU. Again, that's just adding 1.38 to 0.98 and divide it by 2. And that should give you 2.36. Then they ask you for the period in years, and this is the instance where you're going to actually make use of the Kepler's third law. Okay, and I'm going to show you just using one particular calculator key. I'm going to show you how to use Kepler's third law, and everybody should have one of these versions of the calculator key that I'm showing you. So we're going to work it out that way. And again, there's better ways. For instance, you might know about a cube root button, you might know about a cube button, you might know about a square button, and you might know about a cube root button, and that's all well and good. So by all means, use those if you know. But if you don't, I'm not requiring you to do that. I'm just requiring you to use the button that I show you. So we've got here p squared equals a cubed. We now have a, because that's what we just calculated. So what I want to do is I realize that p squared is equal to a cubed means if I have a, I should take and cube it. So I'm going to type in the 2.36. And in this case, I am going to, excuse me, it was 2.36 is what that added to. But when I divide it by 2, I got 1.18. I'm sorry about that. I should have written that as 2a. And then this means a is equal to 1.18 AU. Sorry about that. So scratch that number out again, careless mistake. I'm going to type in 1.18. So that's the calculator button, supposedly. Now, your calculator will have one of these buttons. It'll have a caret key. It'll have an X raised to the Y power key, or it'll have a Y raised to the X power key. One of those 3 buttons will be there. You're going to then follow that up with 3 because we wish to raise this to the 3 power. And some calculators require you to hit equals, some don't. So I'll put a question mark there. And when you actually do that calculation, you'll find out that you get 1.18 raised to the 3 power is 1.64303. Now, if you wanted to do the other one, if you were given, well, at this point, we're going to go ahead and calculate p squared, because now what we have is a cubed is equal to p squared, which equals 1.64303. And I gave way more digits than really necessary here. But what I want is the period. So now I have to do the opposite operation of taking raising something to the square power. So it turns out that can be accomplished by taking the 1.64303. In other words, you don't have to type it back in, but if you erased it, then maybe you do. And again, you use whichever one of these buttons you have, X to the Y, Y to the X, or the caret key. Any one of these 3 buttons will do, but this time we're taking it to the 1/2 power. So that's 0.5. If we were solving Kepler's third law the other way, we would first raise the p to the 2 power. And then secondly, we would raise that answer to the 0.3333333 or 1/3 power. Again, we may or may not have to hit equals. So I'll put a question mark over that. So I'm going to get the answer now, and I get the answer is 1.2818. So 1.2818 is the number of years that the whole orbit would take, but it is actually asking for the, after the orbital period, it's asking for the transfer time. So you just take that number and divide it by 2. So that's a very typical calculation that you're going to have to do in this lab. Dividing that by 2 gives you like 0.641. Of course, then it'll ask you to convert it to days by multiplying by 365. So you just multiply that 0.641 by 365, and that'll give you the number of days in a transfer. Now, the other thing that you're going to have to be able to do is use that velocity is equal to 30 kilometers per second times the square root of 2 over r minus 1 over a. So I want to quickly show you how that's done. So for instance, in the first part, B velocity, in B velocity, they're going to ask you to, in calculations 1, 2, and 3, assume that the spacecraft arrives at Mars when Mars is at perihelion, and assume that at launch time, Earth is at perihelion. So that's that very first orbit we did. And what we want to do is calculate the speed of the spacecraft when it is in the spacecraft's perihelion, in other words, while it's still at Earth. So what that means is I'm going to take 30 kilometers per second and I'll multiply it by the square root of 2. Now we're asking for the velocity at perihelion. So that's when it's actually closest to the sun, which would be when it's at Earth's orbit. And since we're going from perihelion to perihelion, that means 0.98. So I'll go over 0.98 minus 1. Now this is the property of the actual orbit, not of the Earth's orbit, not of Mars's orbit, but of the actual object's orbit. And of course, the semi-major axis of the object's orbit, we found out, was 1.18 astronomical units. So we'll type in 1.18. Now that's all well and good, but I know using your calculator might be a little bit complicated to doing this. So what I'm going to do is I'm going to tell you how to do it. I will type in 2, and then I'll type, make sure you can see it. I'm going to type in 2, and then I'm going to type in divide by 0.98, and then I'm going to hit equals, and I get 2.040816. Okay, now I'm going to do minus. In other words, just leave that right there on the screen. Minus, now I'm going to do a left parenthesis just to make sure I'm being careful with my with my order of operations. I'm going to type a left parenthesis, and then I'm going to type in 1 divided by 1.18. So 1 divided by 1.18, and then right parenthesis. Some calculators just require you to hit the parenthesis once, so be careful with that. So that's the whole thing right there. I hit equals, and that's just everything under the square root, and I get an answer of 1.193359. I'm giving you way more digits just to make sure you got the same thing I did. So now I'm going to take that, and I'm going to take the square root of it. So I'll say, now I'll type in 1.193359, and I'm going to raise it again using one of those 3 buttons that we talked about. I'm going to raise it to the 1/2 power because that's the square root. So I'm going to say, and this gives me 1.09241. Two, 4, 1, 1.09241. Now that's the whole square root thing. So now I just multiply that by 30, and I get 32.77229. 32.77229 kilometers per second. That's the velocity of the spacecraft at perihelion. And what we want to know next is find the speed of Earth, because just by if we just took a crane and dropped the ship up in the air, the ship would already have a speed equal to the speed of the Earth. So in that case, we're going to use for A, we're going to use 1 for the Earth's orbit, and then we're going to use 0.98 for the location of the Earth, and we'll do the same process again. But I think that gives you enough to understand how to complete this lab. So I hope that helps, and that is it. Have a good day.